So hello and welcome back to VHP tutorials. In today's video we will discuss about the heat conduction through single cylinder or hollow cylinder. In previous videos we had completed our video lecture series of heat conduction through plane wall and heat conduction through composite plane walls. In that videos we had discussed about the formula of heat transfer through plane wall and through composite plane walls. We had also derived the thermal resistance formula for the plane wall. So now we will start a new video lecture series on the cylinders. So in today's video we will discuss about the heat conduction through a hollow cylinder, and we will also derive the formula for thermal resistance in case of cylinder. Okay, so without wasting any time, but I've just forgot one thing. So please don't forget to subscribe my channel, and if you have any doubts then please ask me in the comment section. Also follow me on the Instagram. I will provide the link in the description corner. And please, if you find this video helpful, then make sure that you hit the like button. Okay, so without any further delay, let's get started. So now we will start. Consider this a hollow cylinder. Yeah, I know it is not perfectly circle, but you can consider this as an hollow cylinder. So this is the outer wall of the hollow cylinder and this is the inner wall of the hollow cylinder. Now T1 is the temperature of the inner wall and T2 is the temperature of the outer wall of the cylinder. L is the length of the cylinder. This is the front view of the cylinder. So behind this wall there is a cylinder of L length, and the tips of this cylinder are insulated. And R1 and R2 are the radii of this cylinder. R1 is the inner radius and R2 is the outer radius. We are considering the case of uniform K. That means the thermal conductivity of the material of the cylinder is uniform. That means the material of this cylinder is homogeneous and isotropic. Now our aim is to derive the equation of heat conduction. So for that we have two methods, that is by Fourier's law or by general heat conduction equation. In this video we will derive the equation using general heat conduction equations. Means we have three types of general heat conduction equation. That is, first is general heat conduction equation in Cartesian form. Then we have general heat conduction equation in cylindrical form. And third we have general heat conduction equation in spherical form. So as we have a cylinder, so we will use general heat conduction equation in cylindrical form. So if we use this equations, then we have to consider some assumptions. So now, as we know that T1 is the temperature of inner wall of the cylinder and T2 is the temperature of outer wall of the hollow cylinder. Now we are assuming that T1 is greater than T2. So the inner wall of the cylinder is hot as compared to the outer wall. So the heat will flow in the direction of T1 to T2. Now whenever the case of cylinder you encounter, then always consider the direction of heat flow is along the radial direction only. In practical life, there are three different directions for the cylinder. That is along the radial direction, along the axial direction of the cylinder, along the circumferential direction of the cylinders. Means we have three different directions in which we can see our heat is flowing. But on the paper we are considering only along the radial direction. So by default, whenever you see the cylinder, then consider our direction is along radial direction. Now we will see the heat is flowing outside or heat is flowing inside the cylinder. So as our temperature T1 is greater than T2, that means our heat is flowing outwards, means outside. So we will mark a direction. So this is our direction of heat flow Q, that is from inside to outside. Now we will consider certain assumptions. So to use the general heat conduction equation in cylindrical coordinates, we have to consider some assumptions. So first assumption is our direction of heat flow is only in one direction, or we can write we have one directional heat flow, and we are considering radial direction. In other two direction heat is not flowing, we had assumed. Now the second is we have steady state heat conduction. Steady state heat conduction. So whenever we have steady state heat conduction, then the temperature, change in temperature with respect to time will be 0. That means temperature will not change with respect to time. It will remain constant. The whole concept of steady state heat conduction is discussed in the earlier videos of heat transfer. So you can check that videos in the playlist of heat transfer in my channel. So steady state heat conduction means change in temperature with respect to time will be 0. That means temperature will not change with respect to time. Now the third assumption is there will be no internal heat generation. No internal heat generation. That means Qg will be 0. Then fourth assumption is our K is uniform. That is our case. So we will write here K is uniform. Then fifth assumption you can write that material of the cylinder is homogeneous and isotropic. I am not writing here, you can write in your notebook that fifth assumption is the material of the cylinder is homogeneous and isotropic. Now we will not directly apply these assumptions on this whole hollow cylinder. Rather than we will use a elemental cylinder. So for that we will consider an elemental cylinder. So we will take elemental cylinder here. So this is an elemental cylinder of thickness dr and at a distance r from the center. That means the radius or the distance of this elemental cylinder from the center of the hollow cylinder is r. Now we will first write the formula of general heat conduction equation in Cartesian in cylindrical form, and then we will apply these assumptions. So for that I have to rub this part. I hope you had drawn this figure. Please use the rounder. So see, this is the first circle and this is the outermost circle, and then after we had taken a elemental cylinder. So for that we have to draw two circles for the elemental cylinder. Okay, and T1 is the temperature of inner wall and T2 is the temperature of outer wall. Now how this temperature will change we will see in the temperature distribution equation, but for now I have to rub this part. So this is the general heat conduction equation in cylindrical coordinates. The derivation of this equation is always asked in the university exams. So the video related to the derivation of this equation is in the playlist of heat transfer. So if you had not seen that video, then I suggest please go and see that first. Now the equation is del square T by del R square plus 1 upon R into del T by del R plus 1 upon R square into del square T by del phi square plus del square T by del Z square plus Qg by K equals to 1 upon alpha into del T by del tau. This is the continuation of the equation. Now what are the terms? Means the name of these terms is explained in the previous videos of the general heat conduction equation, but here also I will explain briefly that R is the radius, T is the temperature difference, this phi is the direction, that is the circumferential direction, or we can take the axial direction. The Z is the axial direction in our derivation and phi is the circumferential direction. This Qg is the internal heat generation, K is the thermal conductivity of the material, alpha is the thermal diffusivity, T is tau is the time, T is the temperature. Now we will apply these assumptions. So as we have one directional heat flow and that is along the radial direction, so other than the radial direction, all the direction, that means the axial direction and the circumferential direction will be 0. That means the change in temperature in axial direction and change in temperature in circumferential direction will be 0. Why 0? Because in that directions our heat is not flowing. So this will be 0. So as this is 0, so this term will be cancelled. Now this term will be also 0 because this is the axial direction and this is the circumferential direction. And the second is steady state heat conduction. So del T by delta will be 0. So this right hand part will be also 0. Now there is no internal heat generation. That means Qg is 0. So Qg term will be 0. And K is uniform. Now we are getting this much part only. That is del square T by del R square plus 1 upon R into del T by del R is equals to 0. So as we are having only one variable, we can write this as complete derivative. So d square T by dr square plus 1 upon R into dt by dr is equals to 0. So to do further steps, I have to rub these things. So I hope you got these things. So now from this equation, I can bring 1 upon R as common. So I will write 1 upon R outside of the bracket. In this bracket, I will write R into d square T by dr square plus dt by dr is equals to 0. Now, if your math skills are good, then by observing this equation, you will get trigger in your mind that this equation is the answer of some function. So what type of function is it? We have to find. So for that, we will consider, so if you will see, this is the product rule applied in any derivative function. That is, keeping the first function as constant, we had means we had taken the derivative of the second function. Then plus, then after taking the second function as constant, we had taken the derivative of the first function. So this is the product rule of some function. So now we will find. So for that, you have to do this step in rough page. Okay. So let u is equals to r and v is equals to dt by dr. So how you will get that u is r and v is dt by dr only? So that by practicing. So whenever you do more and more practice, then you will find this as the answer of some derivative function. So that can be done by practicing. Now, what is the derivative rule? As we are having r in variable, so we will write here also r. Now we want to expand this by product rule of derivation. So what is the product rule? So first we will keep as constant, then we will take the derivative of the second function, then plus, taking the second function as constant, we will take the derivative of the first function. Now what is the values of u and v? We will put here. So what is u? U is r. What is v? It is dt by dr, which is equals to, what is u? R. d by dr into v is dt upon dr plus v is dt upon dr into u is what? Dr. So dr upon dr. So it is equals to r into d square T by dr square plus dt by dr into 1. Dr upon dr is 1. So this is what? This is our equation. That is r into d square T by dr square plus dt upon dr, which is equals to what? This is the function which we have to find. So this is the answer of this function. So now we will replace this by this. So it is 1 upon r into derivative of r into dt upon dr is equals to 0. Now we know, what we know? That this radius can never be 0. So we will write, since 1 upon r is not equals to 0. So now suppose that if radius is 0, then there will be no cylinder. So radius will not be 0. So the remaining term will be 0. So d upon dr is equals to, means d upon dr into r into dt upon dr is equals to 0. Now we are getting a derivative, means we are getting the derivation of a function is of a function 0. That means the function will be what? Which type of function gives 0 on derivating that function? So that function must be constant function. So if you will differentiate a constant function, then you will get 0. So this function must be constant. So we will write r into dt upon dr is equals to some constant as c1. So this is the notation. You can write c or c1 or c2 or something else. So r into dt upon dr is constant. Why constant? Because the derivative of this function is 0. So that function must be constant. Now what will be the next step? Now we will bring a variable separable form. So how we can bring? Taking dt on one side and r term on the other side. So dt is equals to 1 upon r into dr into c1. So as we have obtained the variable separable form, the next step should be what? Integrating that function. So that step should trigger in your mind that what will be the next step. So the next step will be integrating the above function. So integrating, we will get integration dt is equals to, this c is constant, so we will take out of the integration c1 into integration of 1 upon r into dr. So I will write this here. Now integration of dt will be t is equals to c1 into what will be the integration of 1 upon r? It will be log r. So I will write ln r plus c2. Why c2? Because here we are having undetermined integration or undefined integration. So if we have an undefined integration, then we will add a constant. Term. So this is our equation, and we will mark this as equation as 1. So this is the temperature distribution equation, but in that we have to find the values of C1 and C2. So that values can be found by boundary conditions. But from this equation we can keep this in your mind that as there is a logarithmic term in this equation. Now what is this equation? This is the temperature distribution of the hollow cylinder. Now which type of equation it is? It is logarithmic equation. So we can say from this equation that the temperature distribution in case of hollow cylinder is logarithmic. So this is the important part. Why? Because in plane walls we had seen that the temperature distribution in case of plane walls was linear one, right? So in case of hollow cylinder it is logarithmic. So remember that in case of hollow cylinder the temperature distribution is logarithmic. Now we will find the values of C1 and C2. For that I have to rub these parts. So what will be the boundary conditions? Boundary means two extreme position of any object. So here we are having a inner wall and the outer wall. So the conditions on that walls will be our boundary conditions. So first we will consider at r is equals to r1. Now you can imagine that we are doing all this derivation on that elemental part of the hollow cylinder. Means this temperature T is the temperature of that elemental hollow cylinder. And this R is what? The distance from the center of hollow cylinder of that elemental cylinder. So means we are doing all the process or all the derivations on that elemental cylinder. So at last we will find the value of Q for whole cylinder. But now we are deriving, so we are dealing with that hollow cylinder only. At last we will find the formula for heat transfer for the hollow cylinder, means whole cylinder, not the elemental part. We will find the formula for that whole cylinder. Now at R is equals to R1, that is inner wall, our temperature is what? T is equals to T1. So we will put here, so T1 is equals to C1 into ln R1 plus C2. Mark this as equation number 2. So the second condition will be the outer wall. So at R is equals to R2, T is equals to T2. So T2 is equals to C1 ln R2 plus C2. So I hope I am correct. T1 is equals to C1 into ln R1 plus C2 and T2 is equals to C1 ln R2 plus C2. Yes, I am correct. Now what would be the next step? which step I should do to eliminate this C2 from these two equations. So I will subtract equation 3 from equation 2. So you have to write the whole statement that subtracting equation 3 from equation 2 we will get, but I am writing directly here. Subtracting equation 2 minus equation 3. You have to write the whole statement. Now T1 minus T2 will be, this C1 will be common, into bracket I am write ln of R1 minus ln R2. Then C2 will be cancelled. Now I will bring minus outside. So ln R2 minus ln R1. So T1 minus T2. Now you will wonder why I had taken minus outside. This is only for the form which we want. Means at last we want ln of R2 by R1. So that's why I had brought this minus sign out. If you will put this ln R1 minus ln R2, then this is also correct. But as we have to obtain the form which is given in the textbook, then for that we have to bring the minus sign outside of this bracket. Now as we know that ln of A minus ln of B can be written as ln of A upon B. So we will apply this same rule. So T1 minus T2 is equals to minus C1 into ln of R2 upon R1. Now from this I can get C1 is equals to minus of T1 minus T2 upon ln of R2 upon R1. So I got the value of C1. So I will write here. So C1 is equals to minus of T1 upon T1 minus T2 upon ln of R2 upon R1. Now we will find the value of C2. For that we will put the value of C1 in equation 2 or equation 3. Means you can put either in the equations, or equation 2 or equation 3. I will put in equation 2. So you have to write putting the equation, putting the value of C1 in equation 2, we will get T1 is equals to minus of T1 minus T2 upon ln of R2 upon R1 into ln R1 plus C2. So C2 is equals to, I will bring whole term on the left hand side. So T1 plus, this is minus, so on left hand side it will be plus T1 minus T2 upon ln of R2 upon R1 into ln R1. So this is the value of C2 which we are getting. So the next step will be putting the values of C1 and C2 in this equation. So we will get our temperature distribution in case of hollow cylinder. So T is equals to, what is C1? C1 is minus of T1 minus T2 upon ln of R2 upon R1 into ln R, plus C2 will be T1 plus T1 minus T2 into ln R1 upon ln R2 minus R1. So if you will rearrange this equation, then we will get T is equals to T1 plus T1 minus T2 into ln R1 upon ln of R2 by R1 minus T1 minus T2 upon ln of R2 by R1. Okay. So this is our temperature distribution in case of hollow cylinder. Now if you don't want to remember this big equation, I will give a dimensionless equation afterwards, but before that we will discuss some points related to this equation. So as the first point is, as the equation have the logarithmic part, so our temperature distribution in case of hollow cylinder will be logarithmic. Now the second point, that by using this equation we can find the temperature at any point inside the cylinder, but for that we have to put the distance of that point from the center of the cylinder. So for example, if you want to find the temperature at a point, let's say 6 centimeter, then you have to put the value of 6 where you will put the value of 6. We will put the value of 6. Okay, I forgot to write this ln r1, means ln r. So to find the value of the temperature at point, means at 6 centimeter from the center, so we'll put the value of 6, means you will put the value 6 in this equation, means in this r. So in place of r you will put 6, sorry, and instead of r1 and r2 you will put the values which are given in the equation, right? So you can find the value of, means you can find the temperature at any point inside the cylinder using this equation. Now I will give the dimensionless form. So you must remember that dimensionless form, not this equation, right? This is the dimensionless form of this equation. If you want this equation, then we have to do certain steps after this step, and you will get at last this equation. But we will not consider that several steps because we don't require that steps. We just require this dimensionless form. So if you want to remember this form, it will be helpful. It is T1 minus T minus T1. T is the temperature which we want to know at that point. So T minus T1 upon T2 minus T1 is equals to ln R upon R1 upon ln of R2 upon R1. Right? Now we will, as we have the temperature distribution equation, now we will derive the formula of heat conduction through a hollow cylinder, and that can be done by Fourier's law. So according to Fourier's law, Q is equals to minus Ka dt by dx. This is Q dot. Originally it is heat transfer rate, right? But we are just writing Q only. So Q is equals to minus Ka into dt by dr. Why dr? Because we are considering in our case the radial direction, that is the heat is flowing along one direction and that is along radial direction. So we will write dr. So Q is equals to minus K. Now here area is what? The area which is perpendicular to heat flow we have to write. So suppose we are having the, now we are dealing with what? We are dealing with the elemental hollow cylinder. So we have to consider the area of that elemental hollow cylinder. So suppose we have a element like this. This is an element of the hollow cylinder. The whole part I had not drawn, but we can consider this. So this is the direction of our heat flow, and this is the element of this our hollow cylinder. Now which area we have to write? The area which is perpendicular to this heat flow direction. So this area we have to write. Now what is this area? This area is the area of the elemental hollow cylinder. That means this is the area of the cylinder. Now what is the area of the cylinder? Area of the cylinder can be written as 2 pi into radius, that is r. R is the radius of that elemental hollow cylinder into the length of that cylinder. So minus K into 2 pi RL into dt by dr. Now we have the formula of T. So we will put here d by dr. So the big formula we will write here. So first it is T1 plus T1 minus T2 upon ln R2 upon R1 into ln R1, and then up to this we had completed, minus T1 minus T2 into ln R upon ln of R2 upon R1, right? I think I am right. So now we have to differentiate this function. So as the variable is R and our T is constant, so T will be 0. This term will also be 0, because if you will put the values of R1, R2, R1, T1, T2, this term will be constant. So the one variable is here is R only. This part is also constant. So this will be 0. This will be 0. So we will get Q is equals to minus K into 2 pi R into L, not R1 or R2. R is what? r is the radius of our elemental cylinder, into differentiating this equation. So this minus as it is and this term as it is, T1 minus T2 divided by ln of R2 upon R1 into differentiation of this log. So it will be 1 upon R. Now this minus and this minus will be plus, so I will rub this part, and this 1 upon R and this R will be cancelled. So at last we are getting a beautiful equation of heat conduction through hollow cylinder will be T1 minus T2 into 2 pi KL divided by ln of R2 upon R1. So this is our heat conduction equation in case of hollow cylinder, that is Q is equals to 2 pi KL into T1 minus T2 upon ln of R2 by R1. Now from this equation we can get the value of thermal resistance. Now I will refresh or refine this what is the concept of thermal resistance. Now suppose that we have 2 points, let's say point A and point B, and these points have temperature T1 and temperature T2. Now whenever there is a temperature difference between any 2 points or any 2 bodies, then we can say that between these 2 bodies we have a thermal resistance. That means we have a thermal resistance when we have temperature difference. So this is the thermal resistance. This thermal resistance will come only when we have temperature difference between any 2 objects, any 2 bodies or any 2 points. So we are having a thermal resistance. Now in our case we have a temperature difference between what? Between the inner wall of the hollow cylinder and the outer wall of the hollow cylinder. So we will have a thermal resistance between these 2 temperatures or these 2 walls. So we want to find that formula of the thermal resistance in case of hollow cylinder. So for that we have a beautiful equation or beautiful form, that by comparing that equation with this equation we can get directly, means by any way we can get the value of RTH. So we will find that. So now we will derive the formula, or we will obtain the formula of thermal resistance. So for that we have a beautiful form, that is Q is equals to delta T upon RTH. Now my friendly suggestion is that please study this concept, means how this form had came is discussed in the previous videos of heat conduction in plane wall. So that in part 1 this concept is discussed very clearly. This is called the electrical analogies compared with the heat transfers, right? So we will obtain this form, and this form is very useful. So Q is equals to delta T upon RTH. Now we have to bring this form in the above equation. So for that, here it is the temperature difference. So this is temperature difference, and in denominator whatever will come will be our thermal resistance. So we will bring this equation according to this equation, means we will bring the above equation in this form. So first Q as it is. Now temperature difference is T1 minus T2 in the numerator. Now the remaining thing which is there we will bring in the denominator. So it is what? It is 1 upon 2 pi KL into ln of R2 by R1. Now you can think yourself that what is the formula of RTH. It is very easy. So if you compare these 2 equations, then you will get delta T, RTH. This is the RTH. The denominator part of this equation is our RTH formula of hollow cylinder. So RTH is equals to 1 upon 2 pi KL into ln of R2 upon R1. So my friends, we are getting a very beautiful result of RTH, that is thermal resistance in case of hollow cylinder is 1 upon 2 pi KL into ln of R2 by R1, where K is the thermal conductivity, L is the length, R2 by R1 is the extreme radii. So this temperature difference, or sorry, this thermal resistance decreases with the increasing value of thermal conductivity. Means if we have thermal conductivity, let's say 400 watt per meter Kelvin. Suppose we have K as 400 watt per meter Kelvin, and our RTH if we will find, then it will be definitely less than this, less than K. If K is greater, then RTH will be lower, or vice versa, or RTH is greater than our K is lower. That means more value of K suggests that our material is conductive or it helps in conduction, and the less value of K represents the more value of RTH, and it indicates that our material is insulator or bad conductor, right? So I hope you had enjoyed this lecture. So that's all. I hope you had enjoyed this lecture. I am again repeating that if you have any doubts, then please ask me in the comment section. Okay, so keep learning, keep growing, and be safe. Okay, so see ya and goodbye until next video.